All right, folks, in this video, this is part two of the two-part series covering the exponential and logarithms of complex numbers. And so this time we're going to be looking at the complex logarithm. And the important thing is that going back to college algebra, we know that the usual logarithms and exponentials are inverses of each other. So we're going to incorporate this relationship, but the thing we need to work on is restricting our domain in the complex plane in order to get a one-to-one function, thereby saying that an inverse exists. So let's actually look at the intuition behind the complex logarithm. All right. So so if W is in the complex plane, so if for any W in the complex plane, we want to find a point Z in the complex plane so that Z equals E to the W. All right, so that's the idea behind it. So if W is the point in the W plane, we need to find a point Z in the Z plane such that Z is equal to E to the W, right? So what I mean here is the range, and this here is the domain here, right? So the domain. Okay, so we can look at this relationship a bit closely by just labeling out what Z equals to in terms of polar coordinates. So if Z is equal to R times E to the I theta, right? Then we can express R times E to the I theta. And if we look at W in terms of the real and imaginary components, we'll get this relationship, right? E times E, E to the IV times E to the U on the right-hand side. So R times E to the I theta equals to E to the U times E to the IV, right? So therefore, we'll have these the set of equations here. R equals to E to the U, and V is equal to theta. And since cosine and sine of theta are periodic, if I add a multiple of 2 pi, we would get the same result, right? So n is an integer here, okay? So therefore, we can say, okay, so we can say that u is equal to the natural log of r, and v is equal to literally the argument of z, right? Okay, the argument of z. So now we can look at the definition of the complex logarithm, right? So ln of z is equal to log base e of r. So I'm referring to this quantity here. So this is a real number. So I'm going to label out the natural log of a real number as log base e of r. Okay, plus I times the argument of z. Okay. So from this point forward, little ln of z, this will represent the complex logarithm. Complex log of z. Okay. All right. So for example, okay, try to find all complex solutions of this equation, e to the w equals to 1 plus I. All right, so try to pause the video and see what you came up with as the solutions for z, or natural log of z. Okay, so I assume you worked on this example. So the z is 1 plus I, right? So 1 plus I is in the first quadrant, so here. Okay. 1 plus I. So the radius here would be root 2. 1 squared plus 1 squared equals the square root of 2. And then theta is pi over 4, right? So that's the argument of z, right? But if we rotate 2 pi radians, or a multiple of 2 pi radians, right, we would get the same result. So now we can write out the natural log of 1 plus I. Well, this equals to root 2 plus I times, well, pi over 4 plus 2n pi. N's in integer, right? And so this equals to root 2 plus I times 8. So we'll have pi 8n plus 1 over 4. Okay. So these are the different types of solutions for the natural log of 1 plus I. Okay. Now, the properties of logarithms that you've seen in college algebra would be the same. Okay. But we're going to have to be careful about the principle of logarithms for the principal branch. We'll talk about the principal logarithm in just a moment here. So if z1 and z2 are complex numbers, all right? So this is true. Natural log of z1 times z2 is equal to natural log of z1 plus natural log of z2. This is relatively easy to show this, right? z1 minus ln of z2. And then z is the powers of a complex number, and times natural log of z1. Okay, these are pretty easy to show, right? So and now we're going to talk about the principal value of the complex logarithm. Since we have the argument of z being a periodic function, right? So so if, yeah, so the argument of z, so the yeah, so with the logarithm function, you'll have the same result if we have an angle, and if we rotate it 2 pi radians clockwise or counterclockwise, or even a multiple of 2 pi, right? So what we need to do is we need to figure out a what's called a principal branch. Okay, so as an example, the natural log of 5, right? The natural log of 5 plus 0i. Well, this equals to log base e of 5, right? Plus I times, well, the angle is 0, but also any multiple of pi would work, right? So natural log of 5, well, it's on the real axis, right? It's on the positive real axis, but if I rotate 2 pi radians clockwise, or even a multiple of 2 pi radians clockwise or counterclockwise, I will still get the same number. Okay, I'll still get the same number. So in this case, what we need to do, so n's an integer here. So what we need to do is we need to find a unique value of the natural log of 5. Okay. All right. And that is where n is 0, right? Where n is 0. So when n is 0, that will be the unique value for the natural log of 5, right? So what we need to do is restrict theta in the interval minus pi up to pi. Okay, minus pi up to pi. We don't include minus pi because that wouldn't be a function, right? So, and from here, we will have what is called the principal logarithm. And they label this as capital ln of z. Capital. So this equals to log base e of the modulus of z, or the radius, plus I times capital argument of z. Okay. So where theta is in between minus pi and pi. Okay, that's another way to write out the principal logarithm. Okay. So, for example, so if I compute the principal logarithm for 1 plus root 3i, let's say. Okay, try to compute that value. Okay, so let's actually look at how we would compute the principal logarithm for this complex number 1 plus 3i, 1 plus root 3i. Okay, so the principal logarithm, right? I times theta. Okay, so 1 plus root 3i, well, that's in the first quadrant, so 1 plus root 3i. And then the modulus of z, this equals to 1 squared plus root 3 squared, which is 2, right? So modulus of z is 2. So we'll have, so capital ln of z equals to log base e of 2 plus I times, know what the angle is? Well, if you guess pi over 3, you are correct. So that's the principal angle, right? So we want the angle theta to be in between this range, right? So in this case, it's pi over 3. It's I times pi over 3. So that is the principal logarithm of 1 plus 3i. The principal logarithm of 1 plus root 3i. Okay? 1 plus root 3 times I. Okay. So, all right. So, uh, also, it's important to note, okay, the identities of logarithms for lowercase ln of z are not necessarily true for capital ln of z. All right, since our capital N and the capital natural log of z, it's defined on a specific range for theta, right? So you're going to have different properties that of logarithms that are true for lowercase ln of z, but they are not necessarily true for capital ln of z. So as an example, it's not necessarily true that capital natural log of z1 times z2 it does not equal to natural log of z1 plus capital natural log of z2. All right. Okay. So so we cannot necessarily say this is true, right? So hopefully you keep that in mind. So anyway, but we can still we can define an inverse function for w equals e to the z, right? And and it reflects on using the fundamental region for e to the z. Okay. Capital natural log of e to the z would equal to z if x is any real number and y is in between minus pi and then pi. Okay. So this relationship would be true as long as x is a real number and then y is in between minus pi and pi. So the inverse function of z would equal to the capital natural log of z if f of z is e to the z. Okay, that's the corresponding inverse function, right? Now there's so it's interesting to know about the continuity and analyticity of the natural log function or the principal natural log function. Okay, so let's talk about analyticity of capital natural log of z. Now, so by definition, let me write out the capital natural log of z here real quick. Plus I times the principal argument of z, right? So here is the complex plane, right? Corresponding real axis and the imaginary axis, right? And let's test if the point -1, 0 is continuous. All right. There's a reason why I chose that point, but we'll see here in just a moment. So, okay. So, and we're going to approach, so we're going to look at what this limit of the natural log of z would equal to as we approach this point along a circular path of radius 1, right? So in this case, z is equal to e to the I theta, right? So as you notice, points in the second quadrant. So if I look at the different quadrants of the complex plane, right? So points in the second quadrant, they will approach this point along when theta is pi over 2 to pi, right? On up to pi. So therefore, the points approach to e to the I pi, right? Okay, 1 times e to the I pi. All right. But points in the third quadrant, just to remind you that the principal argument of z is in between minus pi and pi, right? Points in the third quadrant, they will approach this point along argument of z minus pi over 2, right? Along minus pi over 2. Okay. So the points in the third quadrant, so they will approach this way. So that's clockwise. If the argument of z is in between minus pi over 2. So that means the points in polar coordinates, they approach to 1 e to the minus pi, right? And so these values here will be different. They're different. They don't equal to each other. So by the two-path test, the limit as well, theta approaches, as the points in z approach to -1, 0, it does not exist. Okay. So the limit is discontinuous at the point -1, 0, right? But not only that point, but points on the negative real axis. On the negative real axis. So therefore, the principal logarithm of z is discontinuous along the negative real axis. On the negative real axis. So that means a derivative does not even exist at that point, right? Okay, so a derivative for a natural log of z does not exist at that point. Okay, so and okay, so therefore, so the natural log of z is continuous on, we just don't include the negative real axis, right? Okay, so okay, so here, so we are disregarding the negative real axis. So they refer to this as a branch cut. Okay. So this will be a branch cut for the argument of z, right? So not only that, this is what's called the principal branch cut. The principal branch cut. So they label this as F1. And then we can have multiple branch cuts for the natural log of for the natural log of z, right? So we can also define like the argument of z as minus 3 pi over 4 to 5 pi over 4, right? Or so we can, so in other words, we can define other branch cuts for the logarithm of z just as long as the length of the interval for the argument of z is 2 pi, right? So yeah, so minus 3 pi over 2 up to pi over 2. That's another branch cut, right? But the principal branch cut they refer to is this interval for the argument of z. Okay. Because the principal argument of z is it's using the same endpoints as your limits. So that's why they call it the principal branch cut. Okay, so another theorem to write down is the principal branch F1 for, if I look at, they label F1 of z as log base e of r plus I times theta. R is equal to the length of z, and theta is just the argument of z is analytic. And the derivative of the of f1 of z is equal to 1 over z. Okay. Yeah. Okay. And the proof behind this is you're going to use the polar coordinate version of the Cauchy-Riemann equations. And this is the other equation. Minus 1 over r partial v with respect to theta. So you're going to use the polar version of the Cauchy-Riemann equations to show this. So, and then you're just going to let z is equal to some re the I theta. Okay. All right. So, yeah, and then not this, but you're just going to use f1 of z and yeah, use f1 of z. So this is your u component and this is the v component. All right, should be not bad to show this. Okay, so for example, Yeah. F of z is equal to the natural log of z squared plus 1. Okay. This here is straightforward, right? We want to look at f prime of z, where f of z is equal to the natural log of z squared plus 1. Right here, you're just going to use the chain rule. Chain rule time. So f prime of z, this equals to the derivative of the natural log function, right? Which is 1 over z, right? Times the derivative of the inside function, which is 2z. So you have 2z over z squared plus 1. And that's the derivative. Okay? It's the derivative. And then finally, just real quick, I'm going to go over the logarithmic mapping. And then, since we derived that the logarithm and e to the z are inverses of each other, inverse functions of each other, this function's mapping can thought of as inverse mappings of w equals e to the z. So let me show you what I mean by this. W equals ln of z maps the set where the radii of the complex numbers is strictly positive. This maps onto the region in the strip in the W plane, right? So this is exactly like the one of the conditions in mapping the exponential function, right? If you just take any real number x, that number should have a strictly positive radius, right? Okay, because the domain of the exponential function is since the range of the exponential function is any number that's strictly positive, right? This function will map circles onto a vertical line. Onto the vertical line segment, since it's on a region. U equals log base e of r, right? And then v is in between minus pi and pi, right? And finally, this function will map, raise whose r, which is defined as the argument of z equals theta onto a horizontal line, right? V equals theta, where u is just any real number. Okay. So it's literally just the inverse map of the exponential function, right? So for one more example, I want you to think about this example here. Find the image of w equals the principal logarithm of z if Find the image of S using W equals the natural log of Z, where S is this following region. So we have an annulus. So we'll have one of them is the circle of radius 1, and the other is the circle of radius 3. And we have the region that's in between. Okay? The region that's in between. So try and work on figuring out what the image is of this set onto the W plane. Okay, so I assumed you work on this example. So let's see what this image will look like in the W plane, right? So in the W plane, okay, so in the W plane, so we have the circle of radius 1, right? And and so the fundamental region, so this will map to the fundamental region. So so we'll have pi here. So V equals pi, and then we'll have minus pi here. Shoot. Let me do red. Red is no-go. And this is V equals minus pi, right? And so this is the region that we're seeing here. Okay, so we start off at the circle of radius 1. So that means that would correspond to a vertical line segment at u equals 1. All right, so we'll have the vertical line segment u equals 1. And then we'll have the upper circle z equals 3 with radius 3. And that will correspond to another vertical line segment where u is 3. And we want the region that's in between. So literally it's just this strip here, right? This strip here in the UV plane. Okay. So this is the image S prime here in the UV plane. Okay. So that concludes the two-part series of the complex exponential and logarithm. So these are some problems for you to work with. Next time we'll be looking at trig functions in the complex numbers. So 2, 6, 8, 12, 16, 18, 20, 22, 24, 30, 32, 36, 42, 44. This section was quite long. So it's a lot more problems for you to work on. So if you have questions, please let me know. Thank you for watching, and I will see you all in the next video. So take care.